Okay, so freeze.
Yes, so let's go right. I just lost my, oh. So now you can all see my password maybe, no? Oh no, it's not recording anymore. Screen? Yes. Sorry guys, I lost contact with my tablet here. Okay. We're back. So I want to continue making remarks on this solid theory. So the next remark will be, so by construction, Z bracket S solid is equal to, well, this inverse limit of Si, Z bracket Si, for S extremely disconnected, profinite. But this expression, Z bracket S, makes sense for a general condensed set. So you could very well ask what's going on in general. So remark. So the if M is a pseudo-coherent solid abelian group, or a pseudo-coherent complex of solid abelian groups, so just a complex where each term is a compact projective, meaning a product of copies of Z, then you can recover M as the Arhom, the double internal Arhom from M to Z. And these internal Arhoms are all taking place in condensed abelian groups. And it's also the same as in solid abelian groups. And moreover, this guy will be discrete. So this will be a discrete complex of discrete abelian groups, living only in cohomological degrees, but perhaps going all the way down to cohomological infinity. And the reason this is true is, well, you see that it's true for these generators, products of copies of Z, and then you just and then you see that the T, these don't mess up the T structure too much. They're actually T exact, both of these functors on that full subcategory, and then you can control even an unbounded complex. So we can apply this to M equals Z bracket S. Well, let's say the derived the derived solidification of Z bracket S whenever S is a compact Hausdorff space. Because we know S will admit a resolution, what is it called? A hypercover by extremely disconnecteds. Therefore, the derived solidification will be represented by a chain complex of compact projective solid modules. And what we deduce is that ZS, the derived solidification of Z bracket S, is the same as Arhom, internal Arhom from, yes, thank you, a second Z is missing, yeah, double dual. From the Arhoms from the derived solidification of this to Z, but by the universal property of solidification, that is just the continuous functions, the derived continuous functions. I should write, yeah, maybe I should write it out. Sorry, guys. Z. And we saw earlier that we're in Peter's lecture, we saw that this thing is just the sheaf cohomology of the compact Hausdorff space with coefficients in Z. And then you take the, well, sorry, I should say R gamma. R. The derived functor of global sections, which is the usual cohomology. So for example, if we take S to be a profinite set, not necessarily extremely disconnected, then this, well, we know that profinite set is zero dimensional, also in the sense of cohomological dimension, and this is just the living in degree zero, and it's just the colimit of the direct sum of copies of Si. Okay. And then when we dualize back again, we get that the derived solidification of this sits in degree 0, and it's also given by this familiar expression. The same expression as in the extremely disconnected case. So that's no surprise, but it's good to know. A priori, it lived in higher, it could have higher derived functors as well. Yeah, this argument shows that, I guess we also have to use Specker's theorem here to see that there's no, that the R hom from this to Z is the same as the original hom. This is a free abelian group. So by Specker's theorem, the R hom is just the usual hom up here as well. Right, so that's good, but something quite different happens if S is not profinite, but is a compact Hausdorff space. For example, if S is a finite CW complex, then what we get is that Z bracket S solidified it's the dual to the cohomology of S with Z coefficients. But now the cohomology of S with Z coefficients is a finite, finitely generated Z module, basically, or it's a perfect complex of Z modules. So when you take the dual, it's not introducing any inverse limits, no condensed structure. It's just going to be discrete again. It's going to be a usual finite dimensional thing. And you find that this is the same thing as the singular homology, or a complex computing. The singular homology of S with Z coefficients. In particular, it could live in arbitrarily, well, not arbitrarily high degrees. It could, well, if you vary S, yeah, it could live in, it could go up to degree 100. Let's put it that way. Yeah. So you might remember when Peter gave his first lecture, he talked about how, for finite CW complexes, the homology is more important and fundamental, but with sheaf cohomology, all you have is cohomology and it can't have a pre-dual because it's an infinite thing. But actually this Z bracket SL is a good homology. You can think of it as like the homology of S in general for a compact Hausdorff space. It's a good object to think of as homology. It's a pre-dual of cohomology, a pre-dual of sheaf cohomology, which has very good formal properties. And it kind of rescues the idea that homology should be fundamental, despite the arguments that, the arguments that Peter made in the first lecture. Those are based on the idea of having the pre-dual always be a discrete abelian group, but if you allow it to be a condensed abelian group, then there's a wonderful, beautiful pre-dual, and it's this solidification of the free condensed abelian group on S. And by the way, actually, this extends solidification. No, it's homology, not Borel-Moore. No, solidification commutes with colimits. And you can use that to show that this description, same statement is true. True for, what's it called? For arbitrary CW complexes. So if you take an arbitrary CW complex, it is a compactly generated weak Hausdorff space. You view it as a condensed set, take the free condensed abelian group and solidify it. It's discrete. Yeah, you define it by putting things in the condensed world and doing this solidification, but you end up with something discrete, and it's just a chain complex computing the usual singular homology of your CW complex. Quite weird. It's kind of very weird if you think about this. If you try taking this as your definition of singular homology, then apparently what you have to do is you have to take your CW complex and resolve it by extremely disconnected compact Hausdorff spaces, these stone check compactifications of sets. And every time you see one of those, you replace it by an infinite product of copies of Z's. And then that's your chain complex computing singular homology. So it's kind of a miracle that it all works out, but it does. Okay. So there's another thing I want to mention, which is there's a synthetic approach to solid theory. So in fact, anytime you have an abelian category generated by compact projectives, you can just understand HOMs in that abelian, what the objects are and what the HOMs are, just in terms of the HOMs between the compact projectives. So if, let's go back to the situation of ACP subset of A. If this is a compact projective generators, then every object of A, we can resolve it by direct sum of compact projectives, like this. And then we can, if we want to understand maps, so all objects can be parameterized by presentations like this, right? Of compact projectives. Now we want to understand what are the maps from M to N, right? So, well, first of all, we know how to map out of a, so it's enough to map here such that the kernel dies. So it's enough to know how to map out of direct sums of compact projective generators. But then direct sums, again, we can pull out. So it's enough to know how to map a single compact projective to N. But then by definition of compact projective, it commutes, mapping out of it is an exact functor. So it's the same thing as that you take maps from here to here and then take the co-kernel of that, mapping the maps from here to here. And then maps into the direct sum will factor through a finite direct sum, which is again of the same form. A finite direct sum of compact projectives is compact projectives. So it's the maps are, all maps are completely formally determined. By maps between compact projectives. And one way of expressing this is, so if ACP is small, so if we have an actual set, this will tell you that A is the same thing as additive functors from ACP op to abelian groups via the restricted Yoneda embedding. Yeah? So you take an M in here to so that's another way of expressing this same thing that I just explained, that you can just check that the maps are the same in both cases, in other words. So it's a really simple thing. It's just a functor category.
This is Morita theory.
This is Morita theory in a nutshell. Morita theory on many objects, so to speak. Yeah. So now if we take solid, and maybe we're working kappa condensed context, just so that I don't have to, I'll just fix a cutoff cardinal for the sake of it. Then the compact projective generators can be taken to be these products of copies of Z. And if you look at the calculation for how to map between those, it's actually just dual to each map from, one way of expressing that is saying that each map product of Z is the dual of some map, maybe I'll put the I here and the J here so you can see, some map of discrete abelian groups from J to I. If you look at the HOM calculation here, it's exactly the same as the HOM calculation here. So that means that solid Z with a cutoff cardinal kappa is going to be the same thing as additive functors from free abelian groups of on index set of size less than kappa to abelian groups. So it is indeed something that you could have just written down a priori for some other reasons, additive functors from free abelian groups to abelian groups, why not? Yeah, and then you could, the solid tensor product is also very easy to describe because it just comes from the tensor product of free abelian groups, kind of by some sort of day convolution or something like that. And in fact, everything that we do with solid abelian groups, the whole solid theory and all the consequences that we build up, you could just do it from this synthetic perspective and completely forget about the fact that it naturally sits, you could forget that it sits in condensed abelian groups. And just work with this. But you probably don't want to, or there are some reasons you wouldn't want to. So I think the two most convincing ones that we've come up with, that I remember, maybe Peter remembers more, but the two most convincing reasons is that we wouldn't have discovered this solid abelian groups or realized the role it could play if it weren't for the condensed framework that it was naturally living in for us. It would have been very unclear why such a definition was a good one without the condensed framework inside of it. So, and then when it came to the liquid story, I mean, we wouldn't have been able to guess something to put there. We really had to look in the condensed framework and see, have it tell us what the right thing was, like have it tell us what the correct axioms were. I mean, have it tell us what we needed to write down in order to verify these axioms that in this abstract framework, this star condition I talked about in the previous lecture. So the condensed framework is nice because there's often only one thing you can do, like, and then you do it and it works. So that's very comforting psychologically. That's the good thing about condensed stuff, and it led to this solid thing. And if we had just written down this a priori object and worked with it, it would have felt much less convincing. But the other reason you might care about viewing solid abelian groups inside condensed abelian groups is because this way it's very easy to say what you mean by, for example, a profinite group acting continuously on a solid abelian group. So if you're in the, I mean, if you think of it as a condensed abelian group, there's just only one thing this can mean, and it is just the usual thing of like a G action on an object. Yeah, you have a group object in a category acting on an abelian group object in a category. You can just write that down, know what it means. But if you have this thing here, then you might look at this and say, okay, what does it mean to have a solid abelian group acting, a profinite group acting on an object in this category? And then you kind of have to scratch your head a little bit. Or these free things, these Z bracket S's, which connect with algebraic topology, like we discussed. I mean, it might not be so obvious how to see them in here. So anyway, but in terms of applications to algebraic geometry and so on, you should be perfectly happy just taking the what's it called, the synthetic definition, which I've just explained. I know Peter, did I forget?
In the synthetic definition, you could also replace abelian groups with anything. Is that right?
That's correct. You could also, yeah, but then there's an interesting thing which we maintain that that's not the correct thing for a general ring R. So I don't think we're going to get into this week, so maybe I'll say just a couple of things about it. So for a general ring R, yes, you could make the same definition with free R modules, functors from free R modules to abelian groups, additive functors from free R modules to abelian groups. And for general R, that will not embed fully faithfully into condensed R modules. So for finitely generated rings, so for finite type Z algebras, it will, and then that's a good thing to consider. But we maintain that for infinite type rings, that's not the correct thing to use, in fact. And when you realize it's not the correct thing to use, then you also realize that there's flexibility in the choice of the correct thing.
Could you elucidate a little bit? For example, there's linear compactness versus compactness going back 100 years ago for, Lefschetz linear compactness.
Yeah.
So suppose your ring is, let's say, just a big field or a finite global dimension ring, and you do this linear compactness version as opposed to compact. Would it work?
So you can, yes, it would work for your algebraic geometry purposes. You could take that definition of solid K modules, and you'd be able to do everything we do over Z over a general base, basically. But there are some things that you won't be able to do. What am I trying to say? No, I mean, it always works. I don't exactly know what I'm trying to say. No, I mean, it does always work. You can just use it. But you might also, we have this, okay, what am I trying to say? We have this notion of analytic ring structure, which is basically you have a condensed ring R, and then an analytic ring is basically a system, is an assignment of satisfying the axiomatics I pointed out in the previous lecture. So it's a theory with the same formal properties as solid abelian groups. So produced in the same way, where you give an assignment for every compact projective and then check some property, and then you get this nice abelian category. And it's important for making a lot of arguments, especially when you move into formal schemes and adic spaces and so on, to maintain the flexibility of changing the analytic ring structure that you have on your given ring. We were able, I guess what I'm really trying to say is that for all the arguments we've ever wanted to make, we were able to only use these analytic rings, which literally, I mean, the ones that in the framework I explained where everything's condensed, and you don't have to build anything, none of these more general ones that you could build synthetically without putting it in condensed are actually relevant for any arguments. And they might even hamper you psychologically in that it makes it seem like there's a canonical choice for your category of modules, whereas in fact, you're supposed to keep in mind there are always a whole plethora of choices, different possible analytic ring structures. I'm not sure I've explained this very well, but yeah, it's just that we found that the condensed framework sort of points you to helpful concepts, whereas if you try to build something synthetically, you're never quite sure if you've got the right idea. Okay, maybe I'll move on from that since I wasn't explaining it so well anyway. So that's that synthetic approach. Now I want to give a cute application of solid abelian groups, which I'm not entirely sure why I like it so much, but I really do. So who here has heard of Whitehead's problem? It's a problem in abelian group theory from the 40s, I think.
The Scholze counterexample?
Yeah, exactly. Yeah. So let me phrase Whitehead's problem for you. Whitehead asks, is the following true? If A is an abelian group, then whose x1 with z is equal to 0, does that imply that A is free? So the background for this is, well, obviously the converse is true, right? Free abelian groups have no x. Also, abelian groups have cohomological dimension 1, so there can never be any higher x's. And we know projectives are the same thing as frees. So if you had x1a with any other abelian group vanishing, then you'd know this. But the question is whether it's just enough to test it on z. And the answer was given by Scholze. It depends. More specifically, it depends on axioms beyond ZFC. So in other words, there exists a model of ZFC where the answer to Scholze's question, where the answer to Whitehead's question is yes, and there exists a model of ZFC where the answer to Whitehead's question is no. Okay, so you might think that that settles it, but now let me give I'll call it a theorem. The following is true. So let A be an abelian group. Then if the internal x1 in condensed abelian groups from A to Z is 0, then A is free. So note, so if you take the internal, so these are discrete abelian groups, A and Z. Now I'm putting them in this condensed framework and I'm looking at their internal x1 in that framework. But note that the internal x1, it's a condensed abelian group. And its underlying abelian group is the usual x1. So the difference between this version of the statement, which is a true statement in ZFC, in any model of ZFC, the difference between this one and the Whitehead's problem one is exactly this issue of it would be a solid abelian group. Well, it's not just condensed, it's actually solid, yeah? Because the internal R-hom is solid, and then any homotopy group of a solid thing is solid. So the difference between this version and Whitehead's version is exactly the fact that you can have these very non-Hausdorff condensed abelian groups whose underlying abelian group is 0, but perhaps have some exotic values on other extremely disconnected compact Hausdorff spaces. Okay, so let me give a proof of the theorem. Well, let's resolve A by. Was there? Oh no. Okay.
Yeah. Is the theorem true if you have a condensed or solid rather than just discrete?
Well, no, definitely not, because the conclusion says that it's discrete. But
right, but perhaps the vanishing of X implies that it's discrete somehow.
Maybe you want that it's projective or something. Yeah, it sounds like it might be true. Let me not try to think about it on the spot, but it doesn't sound totally unreasonable that if you change the conclusion to being projective, that or something like that, that this might be true for an arbitrary solid abelian group. Okay. Okay. Anyway, so we know that any subgroup of a free abelian group is free, so we can make a two-term resolution of any abelian group. Right, and now so now we'll take Arham, internal Arham from A to Z, and then we get a distinguished triangle, Arham, A, Z, product of I, Z, product of I, Z. So if X1 vanishes, then this is a short exact sequence, Hom AZ, product of IZ, product, oops, there should be a J somewhere. Like this, but in the solid theory, these products of copies of Z are compact projective generators, and in particular, they're projective. So this map exists as splitting. This is a splitting, and that implies that also that implies that Arham, well, Hom AZ, which is the same thing as Arham AZ, is a summand of a product of Z, product of IZ, and then you dualize back again, and you get that A is a summand of the free group, like that. Adrien, maybe this correct thing would be the solidification. You know, you have to have a solid thing in there, or you get a conclusion about the solidification. Yeah. Anyway, so this is the yeah. So this is the proof. So it's a summand, and then again, it's a subgroup of a free group. Therefore, it's free. So this is a little I don't know, somehow. I think it's kind of interesting that we've seen actually in several examples now, I believe, that it can pay to put discrete things in the solid world and look at, or in the condensed world and see what happens there. And I actually tried to make this theorem, you could state it is just about condensed abelian groups, and the X1 is actually somewhat explicit when you resolve. I mean, the X1 is just the co-kernel term in this complex here. So you could try to make it explicit, but actually I was not able to give a very explicit, I couldn't make this proof, I couldn't strip away the solid theory from this proof. The solid theory is really doing something for you. The fact that these are projective, which we only know how to prove by passing from products of copies of Z to products of copies of R to products of copies of R mod Z and so on. So I really, this is a very short argument, but it really does use some of the power of this theory. So, okay. Right, so what do I have? I have 15 minutes. Yeah. So I want to now, I've been telling you about how great the solid theory is and how wonderful everything is, and indeed it is pretty wonderful. But I want to say some things that I want to point to some things we don't know, or yeah. So the there are some mysteries here.
Dustin, I mean, you have 30 minutes, right?
2 minutes. Oh, right. Oh, great. Ah, even better. Okay. Yeah, somehow I got confused. Okay.
Glad to make you happy.
Yeah. So there are some mysteries here. So first of all, I mean, yeah. So one is, well, so we know that these are the compact projective generators. And so, well, you might wonder what the general compact objects are. They're the things that are just co-kernels of maps between these compact projective generators. But what are the possibilities? Look like? It's maybe not so easy to give a description of this category of co-kernels of maps between compact projective generators that doesn't somehow, I mean, doesn't try to reduce to the compact projective generators themselves. And the second thing concerns these product of compact generators. We don't know whether these are flat. Are they? So, i.e., if M is a solid abelian group, is it true that product IZ solid derived tensor product M lives in degree 0? So if M lives in degree 0. Do we know it for countable I? No, I don't even think we know it for countable I. So yeah. So but I want to say that these things, they arise from the fact that these basic objects here are not compact abelian groups. So for the rest of the talk, I want to pass to a simplified setting where you get much nicer properties. So now I want to talk about solid ZP modules. And I'll take the definition to be ZP modules in solid abelian groups. But it's the same thing as, it's actually a full subcategory of solid abelian groups, consisting of those things which admit a ZP module structure. Why? Well, this is because of this idempotency of the solid tensor product of Z with itself. In fact, it's even derived idempotent. Yeah. Again, this is some weird feature of the condensed setting or the solid setting. This kind of behaves sort of like a localization of solid Z, the solid ZP. So the localization is just given by tensoring with ZP. Right. So a solid ZP is an abelian category with enough compact projectives. Namely, well, how do you calculate what the compact projective generators are? Well, you take your compact projective generators for a solid Z theory, and then you tensor them. Well, you do derived tensor product, and then you hope it lives in 1 degree, and it does. We already did this calculation, actually. This is just the product of copies of ZP. So because the derived tensor product lives in a single degree, that will tell you that you have an abelian category with enough compact projectives. And here the problems go away. Here 1 and 2 can be answered. So for 1, the compact objects, which are the co-kernels of maps from products of copies of ZP to products of copies of ZP, are exactly the pro-P. Abelian groups. And 2, product of copies of ZP is flat for the solid tensor product. And you can do the solid tensor product over either Z or ZP. Again, the answer is going to be the same. because ZP is idempotent over Z with respect to the solid tensor product. Right.
Some kind of Nakayama lemma in the solid context.
Yeah, well, I mean, here we're, if you were thinking about number one here, right? Or, well, in any case, I mean, yeah, once you're in the setting of pro-finite abelian groups, then yeah, you can use some normal topological Nakayama lemma to do a lot of kinds of arguments like this, indeed. Right. So by the way, one consequence of one is that this abelian category of solid ZP modules, it admits a somehow even more convincing, what's it called, synthetic description. It's actually just the ind category of pro-P abelian groups, which in turn is the ind category of the pro category of finite P abelian groups. So that's, yeah. So here you don't have to, it's not just the compact projective generators that are nice, but sort of all the compact objects are nice. And then you get a good description like this. So that's fine. And how, so let me explain how to prove two. Right. So we want to know that if you take a product of copies of ZP and you derive solid tensor product with an arbitrary M, we want to know that this lives in degree 0. So by 1, I suppose, we can assume M is pro-P. Because yeah, filtered colimit of things living in degree 0 will again live in degree 0. But then this will just be the infinite product of copies of M. As you can prove by resolving M in 2 steps by infinite products of copies of ZP and using that each of those you can pull out the infinite product with. So if M lives in degree 0, then so does infinite product of copies of M. I guess this is again because infinite products are exact. So that's very nice. Right. Yeah, so a corollary of 2, a more general version of 2, which is a corollary, is that if M is a quasi-separated and P torsion free. Oh no, I just put it. Oh well, it doesn't matter. Oh no. What is this? Too complicated. I don't know how to. It's not letting me write anymore.
Try to go back. Try to push the go back button.
Like this? And keep pressing it until it's back to normal? Oh, okay, thank you. If M is quasi-separated and P torsion free, then M is flat. So e.g., if M is a quasi-separated QP module. So when we get to non-Archimedean functional analysis, if you take any ordinary thing like a Banach space or a Fréchet space, it's going to be flat in this world of solid tensor products. So you don't have to worry about derived tensor products and ordinary tensor products agreeing when you plug in usual things. Okay. So what else do I want to explain? Well, maybe I will explain this interesting remark that came up in the break. So let's do another example of calculations of, sorry. While we're in the ZP world, so, well, So solid ZP modules, all right, so no, well, let me note that there is no P completion condition. On a solid ZP module. A solid ZP module does not need to be p-adically complete. For example, I was already just talking about QP vector spaces. So these are ones where P is invertible. So it's the exact opposite of P being complete in the adic sense. And so what I mean is this. However, we can consider that full subcategory. The full subcategory of the p-complete solid Z modules, which is the same thing as the p-complete solid ZP modules. They'll all be modules over ZP. And this is, well, this is closed under all limits. Sorry, I want to take actually, I want to take derived p-complete things. Yeah. So if you're not familiar with this concept of derived p-completion, it's basically the same thing except you derive everything. So R should be the R lim of the M derived mod p to the n, which is the cone of multiplication by p on multiplication by p to the n on m. And it's just much more convenient. So when there's no p torsion, when there's a bound on the p torsion in M, it's the same thing as being complete in the ordinary sense. But for all sorts of general arguments, it's just much more convenient to work with derived p-complete things and then check at the end whether there wasn't some unbounded p torsion screwing things up. For example, derived p-complete abelian groups or solid abelian groups, or in any kind of context, they form an abelian category. So they're closed under kernels and co-kernels. Whereas if you look at the usual p-complete condition without the derived, then that's not true. And also you can make this condition for complexes or elements in the derived category. And then an object in the derived category will be derived p-complete if and only if each homotopy group is derived p-complete, not ordinary p-complete. So it's much more convenient to work with derived p-complete things. Anyway, this is closed under all limits. Actually, maybe I'll pass to the derived context right now. And I'll stick with the homologically greater than or equal to 0 part. Not all colimits, but, and this is a bit of a surprise, it's closed under the solid tensor product. So in other words, if you take two p-complete things and you want to understand their derived tensor product, it's going to be p-complete. So in particular, it'll be the derived inverse limit of the m mod pn tensor solid over z mod pn n mod pn. So you can often reduce, basically can reduce to understanding m mod p tensor over fp n mod p. And this is really convenient for calculations. You don't have to always re-express such a thing in terms of these compact projective generators and do the calculation. You can just reduce mod p to the n and calculate it there. So for example, if you take an infinite direct sum of copies of z and then p complete it, and you do the solid tensor product with an infinite direct sum of copies, another infinite direct sum of copies of z, and then p completed, you get the infinite direct sum of copies of I tensor z, p completed. So these are so these are your basic p complete things. And this shows they tensor product the way you'd expect. This is the kind of completed tensor product you'd expect if you're used to working with derived p-complete objects. And actually, instead of giving the argument for the full claim that the derived tensor product of two p-complete things is closed under p-complete, things, let me give just the proof of this example, which already is sort of contains the general idea. So this will, so what we have to do is somehow write this thing, this p completion of a discrete thing, in terms of these compact projective generators. And how can we figure out how to do this? Well, note that, well, if we want to understand this condensed set, then we just have to think about what maps from a profinite set are to it. Well, so this is the same thing as compatible maps from S to direct sum of copies of Z mod P to the N. And every map, this is now a profinite set, and we're now mapping it to a discrete set, mapping it continuously to a discrete set. Therefore, it's going to have finite image. So when you map this profinite set in modulo any power of P, you're only going to be hitting finitely many components. So what this is saying is that in here, the p-adic valuation of the image has to tend to infinity with the index set. Because when you, and if you think about what this means, it's telling you that as a condensed set, the way you write this in terms of compact, well, you can write this as a filtered union over all. So you say how big you want you allow the p-adic valuations to be. So right to n union infinity, functions f from the index set to n union infinity, which tending to infinity as outside finite subset.
These are decaying functions, sometimes called.
Sorry?
Adically decaying functions from S.
Decaying functions, yeah. Maybe I should map it to R greater than or equal to 0 instead, and then I can call them. Yeah, maybe that's better. Oh no. How do I write? Yeah. How do I find my eraser here? Let's see.
No, this is good.
No, I think I'd rather write. I think I prefer absolute values to valuations. I think so. I'll write it like that instead. Yeah. Oh no! Oh darn. Yeah. So I'll go to R greater than or equal to 0. Decaying. So of so the part where you're less than or equal to F, and the part where you're less than less than or equal to F, was that what I wanted to say? No, now I've confused myself, right? It should be greater than or equal to F.
Normal valuation.
Yeah, exactly. I switched from one to the other, and then I got confused about whether I was supposed to say less than or equal to or greater than or equal to. Yeah, I want norm, so I think maybe I got it right. Yeah. But maybe I did want valuation after all. Sorry, guys. This must be getting annoying for you. Anyway, well, the point is, if you look at what each one of these terms is, it actually becomes a product of a copy of ZP instead of a direct sum of the copies of ZP. No, actually, sorry, I want to switch back. There was a reason I did it that way. Tends to infinity as I tends to infinity. And I'll say greater than or equal to F. And so this is the same thing as you take product over I and I of ZP times P to the F of I, so to speak. So this subset here, this condensed subset here is the product over ZP of this scaled copy of ZP, which is just isomorphic to another product of copies of ZP. So then you have to take the tensor product. Take the tensor product of this with itself. and you get, oh no, I switched back, yeah. Right, P the Fi plus Gj. And then what you have to argue is that this index set, this filtered colimit here is cofinal in union over all H, I cross J to n union infinity. So the same thing for the product set. Yeah, so that's not too difficult to see. That any such function can be bounded by something which only depends on this, the sum of two functions, one of which only depends on this variable and the other of which only depends on this variable. So I'll leave it there, but that's the kind of thing. Yeah, so you often have to, so not shockingly at all, to calculate these kind of solid tensor products in examples, you have to control growth conditions. And this is the most basic way in which, most basic instance of that showing up. Right. Okay. So I do have some time left over. I guess I have 10 minutes. So maybe I should go back to the proof that the solid theory exists and give the argument for the general case. So let's verify that the solid theory exists. So we need this star condition. And I'll choose the version with the complexes. If we have a complex m dot, so that's going to be m0, m1, dot, 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 where each term is a direct sum of copies of a product of copies of Z. Then we need that Rhom from a product of copies of Z to this m dot is the same thing as Rhom from Z bracket S to this m dot. Or basically, we need to control this Rhom from the product of copies of Z to this complex. Now, we did this already for m in degree 0. And then since we controlled the Rhom there, that implies that we get it also in the bounded case. Now we can consider the stupid truncation, the so-called stupid truncations. So I'll call it m greater than or equal to n, mapping to m, and then the rest of the term in the triangle is m less than n. So this is a bounded complex, so here we're okay. We want to control Rhoms into here. We can fix a homological degree we're interested in. And then you see that it'll be enough to show that, that Rhoms from our guy to this m greater than or equal to n lives in degrees at most, e.g. n minus 2. And I think maybe we'll even get n minus 1. But if you know that this part, so the Rhom from arhom to m is approximated by the arhom to m minus n, and the discrepancy is the arhom to m greater than or equal to n. So if you can bound the effect of that the cohomological effect of that thing there, then in any fixed degree, if you make n big enough, you'll see that the x from there to m is the same as it from there to m less than n, and we've already controlled that because it's a bounded complex. Okay, so it's enough to see that the so to speak, the cohomological dimension of these complexes is at most 1. Or I wrote 2. I don't know. I'm just giving myself some extra breathing room. It's fine if it's just a constant. So we can also shift. We can shift. We don't have to worry about n. It's just up to shifts. We can move everything down to 0. So then it's enough to show that there are no so for say our original m, now we've just got a special case of our original m equals 0 for I bigger than or equal to 2. So you don't have too many x. Or sorry, I should say no, maybe that's correct, yeah, or I bigger than or equal to 3 or something. Okay, so what do we do now? Now we take the non-stupid truncations, the Postnikov truncations. So m maps to tau less than or equal to nm, tau less than or equal to n minus 1m, etc. And we know we can pull the x's. We can, the x to m will be calculated by some derived inverse limit of x into each of those. So in theory, it suffices to control the x into each of these, but not just in theory, but in practice. It suffices to control the x into these. And these are complexes. Recall that these are the complexes, complex with the same terms as m, except in 1 degree, in a single degree, the top degree, I guess, n where it's a kernel of a differential. So again, by the same kind of devisage, we can control the arhoms into this complex if we can just control, because we understand the arhom statement for all the terms of the complex, it suffices to control the arhoms to the kernel of the differential. So the upshot is we need that to control the x from product of copies of z to the kernel of the differential for I say bigger than or equal to 2 or something like this. Okay. So now let's analyze this complex, this kernel of this differential. So we have our complex. So we have the differential dn, and we're interested in the kernel here. Now the first remark is that we can manipulate this differential formally. So this is a map from direct sum of products of copies of z to direct sum of product of copies of z. We can pull out the direct sum, so to speak. It's just a collection of maps from products of copies of z to direct sum of products of copies of z. And we already argued there that even for arhoms, you can pull in the product of copies of z mapping to direct sum of products of copies of z. So, well, first of all, this kernel is going to be the, we can get rid of the direct sum. So this is going to be a union of things with the product of copies of z mapping direct sum of product of copies of z. And this will be actually a union of product of z mapping the product of copies of z. So we've already argued about mapping targets with this target, so we can sort of formally do all this thing. So if we want to control the x, no, I guess we don't know we can pull the x out here yet. Or do we? Wait a second, I'm getting lost in the train of the argument here. or maybe I don't care about X yet. I'm just noting that the differential, forget about the kernel. The differential itself is formally determined by, it's some infinite matrix where the entries are maps from product of copies of Z to product of copies of Z. And this implies that we can extend dn to product of copies of direct sum of copies of R, direct sum product of copies of R using the same matrix. Oops. So we have a direct sum product of copies of Z, direct sum product of copies of Z there. In fact, this extension is unique. Because right, so if we wanted to know, we want to be able to extend this diagonal arrow along this map, the discrepancy is going to be controlled by something coming from the cofiber term in the sense of triangulated categories. So if R-hom from the cofiber term to here is 0, then we do get a unique extension as desired. And the cofiber term is given by this business with R mod Z's. And there indeed, we know this is pseudo coherence. We can pull out this direct sum, this turns into a product, and then it reduces to the fact that Peter covered that R-homs from products of R mod Z to R is 0. And that implies actually that these DNR are organized into a complex. Meaning they square to 0. When you compose two consecutive ones by this uniqueness statement. So then we can do this switcheroo. So we have actually the whole complex we can write as so we have our complex M, and then we have the complex, so to speak, tensored with R, and we have the complex with R mod Z coefficients. And it's enough to bound the X groups, product of copies of Z, mapping to the kernel of the differential with R n differential with R coefficients, and the n differential with R mod Z coefficients. Okay, so now let's take a deep breath. Right, so let's first talk about the case with R mod Z coefficients. So here, I already said that the differentials are, formally extended from products of copies of Z via pulling out direct sums. Right. So wait, this is going to be some kernel of direct sum of product of copies of R mod Z mapping to direct sum of product of copies of R mod Z. And then yeah, we know that this behaves like a pseudo-coherent object with respect to any of these because, oh no, wait, sorry, R maps to R mod Z. Oh, I'm kind of losing the trail of the argument here, but I think I'm also going over time, which is probably not good. Well, I think I'll have to cut my losses, but let me explain what the point is here. The point is we couldn't control what the kernels of products of Z mapping to products of Z look like, because product of Z is just a weird topological abelian group. But we can control what kernels of products of R mod Z mapping to products of R mod Z look like, because that's just another compact abelian group. And we can re-resolve it by products of copies of R mod Z in such a way that we get a two-term complex. And then there we'll be able to control the X's out. And then similarly, products of copies of real numbers, well, it was formally determined by some matrix. So it's actually the R linear dual of some map from direct sum of R to R. And again, linear algebra over R is easy, so we can factor that as a split surjection followed by a split injection. And that means we can control the kernel. It's also just going to be some product of copies of R. And then so that we understand, and we can bound X from there as well. So we use this same switcheroo again to avoid having to understand kernels of maps between products of copies of Z. which we can't, and switch to products of copies of R and products of copies of R mod Z. I apologize for fluffing that up and going over time. Thanks for listening.